We're actually going to go to 7.7. We're going to skip chapter 4, and we're going to go straight to 7.7. This is the last part of your book about derivatives. So 7.7, this is very important. This is called L'Hopital's rule, which is very often used, on the AP test. Can you hold your questions for later, because we really have no time. Okay, it's called L'Hopital's rule. L'Hopital's rule. We're going to use this all the time now after I show you. Okay, so recall this question in chapter 1. Limit as x goes to 1 of x squared minus x over x squared minus 1. Okay, what happens if I plug in 1? It's not undefined. 0 over 0. 0 over 0 is not undefined. It's called indeterminate form. So what happens is we can do the limit of the numerator. So that's going to give us 0. The denominator, x squared minus 1, that's going to give us 0. So then this actually becomes the 0 over 0 form. 0 over 0 form is called indeterminate. So we cannot determine. So indeterminate. This is not undefined. This is not undefined. Undefined means there is no answer. This one possibly has an answer. So you cannot say they're the same. And very important, you want to write this as an arrow not equal to, the limit is not equal to 0 over 0, because 0 over 0 is indeterminate. It cannot equal something. So please do not write an equal sign. Now, when we were in chapter 1, when this happened, what we did was we factored. Right? So we took out the x in the numerator, and then we factored the denominator, and then we said that cancels. And then we got limit as x goes to 1 of x over x plus 1 was really the simplified version. And then from there, we plugged in 1, and then we got 1/2. So then we said the limit was actually 1/2, right? Now, we're going to use this thing called L'Hopital's rule, which is the faster way of solving this. Okay, so this is the important part. Okay, L'Hopital's rule. If f and g are differentiable, what does it mean by differentiable? Continuous and there is a derivative. Okay, it's continuous and there's a derivative, and g prime of x is not equal to 0 on the open interval that contains a, except possibly at a. If f and g are differentiable and g prime, so the derivative, is not equal to 0 on an open interval that contains a, except possibly at a. Okay, and then limit as x goes to a of f of x is equal to 0, and limit as x goes to a of g of x is equal to 0. We're talking about a function that looks like this, f of x over g of x. So if you have a function where it's f of x over g of x, both of them, if you think of them as separate functions, the numerator is a function, the denominator is a function, we're saying that both functions are continuous and differentiable. And both of them, when you're trying to evaluate at a, both of them go to 0. Or both of them at a goes to plus minus infinity. So that's another possibility where they don't both go to 0. I'm sorry, that's g. They can both go to plus minus infinity as well. Then you establish the indeterminate form. The indeterminate form is the limit f of x goes to a of f of x over g of x is an indeterminate form. of 0 over 0 or infinity over infinity. So when you have a limit of some kind of function over a function where the top goes to 0, bottom goes to 0, or top goes to infinity, bottom goes to infinity, we call that indeterminate form. So we can't figure out what the limit is. If that happens, then L'Hopital's rule says, so you're going to use L'Hopital's rule, then the limit as x goes to a of f of x over g of x, bless you, is equal to the limit as x goes to a of f prime of x over g prime of x. Okay, what it says is if you have two functions f and g, they are both continuous and differentiable. And when you evaluate them at this point a, both of them turn into 0, or both of them turn into infinity. Then what you can do is find the limit by taking the derivative of the two functions separately. So the limit of this f over g is the same as the limit of the derivative separately. Okay, so I'm going to show you how to do that. Yes? If it's not indeterminate form, you can't do it. It has to be in indeterminate form. If it's not indeterminate form, we'll check. Okay, sorry, so yeah. Okay, let's look at this first one. This was in the indeterminate form, right? Okay, top goes to 0, bottom goes to 0. So according to L'Hopital's rule, the limit is the same if I just take the derivative. So what is the derivative of the function on the top? 2x minus 1. What's the derivative of the, okay, 2x. Okay, then I plug in 1. 2 times 1 minus 1 over 2 times 1. That is 1/2. So this is the fastest way to solve this problem if it meets the requirement of L'Hopital's rule, where it's an indeterminate form. You take the derivative of the top, take the derivative of the bottom, plug in the number, and then that's it. Okay, let's try a few things, and then I'm going to tell you how to make sure you write it correctly. But let me show you why L'Hopital's rule works first. Okay, so really quick proof because you may need it in the future in case they give you really strange questions on the test. Okay, so let's say you have two graphs or two functions. This is f, and let's say this one is g. And this point here that they intersect is a, and you can see that they're both intersecting at 0. So then we're asking the question, limit as x goes to a of f over g. Okay, when f is going to a, when x is going to a, what number is f? When x is going to a, what is the function f? 0. So this is going to 0. When x is going to a, what is the value at g? 0. So this is indeterminate form, right? 0 over 0. But remember yesterday, we talked about local linearity. We said if the function is continuous, then what we can say is we zoom in so close that it's almost like a linear line, right? You remember this from yesterday? Okay, so what we can do is write the function as if it's a locally linear line, the tangent line from yesterday. Do you guys still remember that? Yeah. Okay, so then f of x is equal to, so kind of using the formula from yesterday, it's f prime of a times x minus a plus f of a. the linear equation from yesterday. Okay, g of x is the same thing. G of x is equal to g prime of a times x minus a plus g of a. Remember from yesterday, m is equal to f of x minus f of a over x minus a. That's equal to f prime of a. So if we were to solve for f of x, we would multiply both sides by x minus a. And then we add f of a. Do you remember this? Okay, so what we're going to do now is plug both of these into this definition, into the limit. However, I wrote this wrong. That should be 8. What value is f of a? Look at your graph. 0. What value is g of a?
0.
So those two are gone. They're zeros. So let's plug it in. Limit as x goes to a of f of x now becomes f prime of a x minus a. G of x becomes g prime of a x minus a. You can see that cancels. So then this limit becomes that. Therefore, L'Hopital's rule works or agrees. So that only happens when it's differentiable, right? It's differentiable, meaning that point is almost like a straight line. Then you can use this because you're saying it's so close, you're creating a tangent straight line. Then that works. Okay, anyways, this is a proof of L'Hopital's rule. You may need it for something later. I don't know. Just letting you know. Next, let's actually use it. All right, we're going to be very particular in writing this. All right, so go ahead and write down this problem. I'm going to show you how to solve it correctly so that you're going to write this every single time on your homework. So write this question down first. Okay, first, try to evaluate it in your mind. Put 1 in. What do you get? 0 over 0. All right. When you see 0 over 0, think L'Hopital's. Now, you can't write 0 over 0. The AP test will be very strict. They will say wrong. So you can't write 0 over 0. The only way you can do is you need to evaluate the limit of the upper function and the lower function separately. So you're going to write limit as x goes to 1 of natural log x is equal to 0. Limit as x goes to 1 of x minus 1 is equal to 0. So you are proving that the top and bottom go to 0 separately. You're not going to write equals 0 over 0. Okay? Next, you're going to say L'Hopital. If you don't say L'Hopital and you just take a derivative, they're going to say why. Why did you do that?
They already know.
They don't know what you're thinking. All right, you're going to take the derivative now. So limit as x goes to 1. What is the derivative of the numerator? 1 over x. What is the numerator derivative of the denominator? 1. So then if you plug in 1, what do you get? 1. So then the derivative or the limit is 1.
That's so nice.
Yeah, I mean, this problem would not be possible for you to do without a calculator, without L'Hopital's rule, because you can't actually figure out what that number would be. All right, let's try another one together. Okay, x is going to infinity now. In your mind, evaluate. What number is it? Infinity and infinity. So we're going to use L'Hopital, but we got to prove that we can. So limit as x goes to infinity of natural log x is going to infinity. limit as x goes to infinity of square root x is going to infinity. Infinity over infinity means we're going to use L'Hopital.
Can we?
No.
I cannot read your mind.
Can
Okay.
we, just plug it in, whichever one is bigger?
Oh, yes. There's a lot of times where you don't need to use L'Hopital, like you said. So in the numerator, that's a natural log function. It's rising very slowly. Square root x is going to rise faster. So what do you think the limit is?
0.
Yes, the limit will be 0. But if it's not a multiple choice, you have to prove. And to prove, you got to use L'Hopital. If it's a multiple choice, of course, just think about it. 0. Okay, we're going to use L'Hopital on this one. So limit as x goes to infinity. All right, how do I apply L'Hopital? Derivative. So natural log derivative is 1 over x, and derivative of square root x?
1 over square root x.
2 square root x. Okay, so now this is limit as x goes to infinity, 1 over x times 2 square root x. Right? Okay, now, okay, we can plug in infinity right now if you want to just evaluate, or we can do one more step and make it very clear why it is going to be 0. So in the numerator, it's x to the 1/2. In the denominator, it's x to the 1st. So, so 1/2 and 1, that means it goes to the denominator like this, right? 1 minus 1/2 is 1/2 in the denominator. Okay, now if you plug in infinity, 2 over infinity is 0. Are you guys okay?
Infinity at the very first step or no?
Very first step?
Yeah.
Like in the question?
No, right here.
After
After
El
L
Hospital.
top. Yeah.
Here?
Yeah. But isn't
It's going to be 0 over 0. Right? 1 over infinity is 0. 1 over infinity is 0. So that's still going to be,
0.
yeah, I mean, indeterminate, and then you have to do something else with it. Okay, let's have you guys try this one. This one is a little tricky.
I don't remember 25.
Okay, so what are your thoughts?
0 over 0.
It's not equal to 0 over 0. What is it equal to?
Undefined over -1.
Undefined over -1. So what is it?
Undefined.
Undefined. Okay, you can only use L'Hopital's rule when it's 0 over 0 or infinity over infinity when it's an indeterminate form. This is just negative infinity, in fact. So remember, it's going to 0. That means y is going down.
it's negative infinity?
Remember, your natural log graph looks like this. When it's going to 0, it's going down.
So it's not undefined?
Negative infinity and undefined mean the same. Okay, hold your questions. Next one. Try this one.
Oh man, I read that as stain.
Me too.
All right, if you plug in 0, what do you get?
You get
Okay, limit as x goes to 0 of x minus sine x, that's equal to 0. Limit as x goes to 0 of x minus tangent x is equal to 0. L'Hopital.
oh.
All right, limit x goes to 0. All right, what's the derivative of the top?
1 minus cosine x.
1 minus cosine x. What's the derivative of the bottom? Hope you remember.
1 minus secant squared x.
Secant square x. Plug in 0, what do you get?
0 over 0?
1.
0.
0 over 0. What do you do?
Continue. Do it again.
Do it again.
You do it again?
You do it again. Limit as x goes to 0 of 1 minus cosine x is 0. Limit as x goes to 0 of 1 minus secant square x is equal to 0.
Hold up. Wait a minute. Secant squared. Wait, is there a point where we stop?
You will get to a point.
What is this guy's name?
We're waiting for you, Zach.
Hospital.
It really means a hospital.
It doesn't?
No, it does.
Oh. All right, take the derivative. What do you get? What's that? Sine x?
That sounds that's bad.
Sine x. Yes, you're right. Over derivative of 1 over minus secant squared. People are like, I don't want to take the derivative of that.
Oh, I
Yeah,
1 minus secant squared.
No, the one
That's
goes,
a-
the one goes away.
1 goes away. Thank you, Ben.
Yeah, I can see up there.
So it's just negative secant squared.
No, it's negative 2 secant x, right?
Oh.
Power rule, and then now derivative of secant.
Secant plus tangent.
Secant tangent.
Secant tangent, yeah.
Will this never end? All right, plug in 0.
Oh no. Oh no. Oh
This is 0 again. 0 over 0 again. Oh my gosh.
Wait, so this is just going forever?
No, it's not gonna go on forever.
Are you
It's
sure?
gonna end in the next one because derivative of cosine sine is what?
Cosine.
Cosine, and then if you plug in 0, you finally get a 1 and not a 0. Ugh, this problem is a little longer than I thought. Let's skip it. Let's go on to the next one. I think I think what we could have I think what we could have done here was we could have simplified it in a different way. So we don't continue doing L'Hopital's rule.
Yeah.
Right? Cosine and secant.
Yeah, this was a little longer than I thought.
It's like obviously it's gonna be 0.
Zach is in favor of us skipping. All right, let's go to the next one. All right, let's do a nice one. Let's do this one. All right, this one is also easily done without L'Hopital's rule, right? The top is increasing very fast because it's exponential. The bottom is just a parabola. So this is definitely going to be infinity. You can also use L'Hopital's rule to prove that it's infinity.
Yeah.
I am going to not show you because you know how to do it. If the question is not an FRQ, like you don't have to write it, you can just say infinity. It doesn't really matter. If it is, then you have to show your work. Okay, one more like this. Not the last one, but last one of its kind. All right, what's your answer?
We don't know.
0.
Yes, 0.
Can you explain?
Do it.
Yes, just plug it in. So sine of pi is 0. Cosine of pi is negative 1. This is 0 over 2, so it's 0.
How convenient.
It is quite convenient. All right, next one.
What? There's more?
There is more.
Wait, there's one.
All right. There are other kinds of indeterminate form, not just 0 over 0. For example, if you see 0 times infinity, what number is that?
0.
No, it's not 0 because we don't know if it's really going to be 0 or something else. Because when we say infinity, it doesn't really always mean infinity. It could be. Okay, well, let's try this. Okay, so if you plug in 0, what do you get?
0. And undefined.
All right, everyone just want to say 0. Okay, 0 times undefined. Okay, so we need to use L'Hopital's rule. Except we cannot use L'Hopital's rule unless it's in the indeterminate form. It's not this way, correct. So what we have to do is we have to force it to look like that. So what we're going to do is we're going to change it. So it is natural log x over 1 over x. This way, if you plug in 0, what do you get? Negative infinity over undefined, so like infinity. So basically, what we're going to get is limit as x goes to 0 plus. This is equal to infinity. And then, negative infinity. And then limit as x goes to 0 plus of 1 over x is equal to infinity. So that tells me that we can use L'Hopital's rule because it is infinity over infinity. So we're going to use L'Hopital's rule.
I thought 0 divided by infinity was is that another?
0 over infinity is 0. All right.
L hospital.
Limit as x goes to 0 plus.
0 over infinity 0.
Okay, what is the derivative of natural log x? 1 over x. What is derivative of 1 over x?
Negative 1 over x.
Negative 1 over x squared.
Negative.
Okay. Limit as x goes to 0 plus 1 over x times negative x squared. Negative x
What?
Yeah, that makes sense.
Oh, okay, I see.
is 0. So the limit is 0. So in this case, yes, the 0 times infinity is going to be 0, but we had to prove that we did arrive at that answer by, by showing that it is invariably 0. Okay.